Question 6, Part A. We're told to start with the identity cos A plus B is equal to cos A cos B minus sine A sine B. And we're asked to use this to show that cos 2A can be written as 1 minus 2 sine squared A. Let B be equal to A. Then we have cos A plus A is equal to cos A minus sine A. A plus A is 2A, so this is cos 2A, and this is cos squared A. Take away sine squared A. Then we use the fact that cos squared A plus sine squared A is the same as 1, which means that cos squared A must be equal to 1 minus sine squared A. Substituting this in here, we get cos 2A is 1 minus sine squared A. Take away sine squared A, and that's 1 minus 2 sine squared A, as required. In Part B, we're given the equations of two curves. Curve 1 is y is 3 sine 2x, and curve 2 is y is 4 sine squared x. Take away 2 cos 2x. We want to find the x-coordinates of the points where C1 and C2 intersect, or at least we want to find an equation which would give us those x-coordinates. We can see that what we're after is the intersection between these two curves, so we need to solve them simultaneously. Since they're both y equals, we can simply write down 3 sine 2x is equal to 4 sine squared x, take away 2 cos 2x. Now from Part A, we know that 2 sine squared A is equal to 1 minus cos 2A. And that must mean that 4 sine squared x is the same as 2 take away 2 cos 2x. So we can replace the 4 sine squared x just here. That gives us 3 sine 2x is 2 take away 2 cos 2x, take away 2 cos 2x, and that gives us 3 sine 2x is 2 take away 4 cos 2x, which we could rewrite as 4 cos 2x plus 3 sine 2x is equal to 2, as required in the question. In Part C, we want to express the left-hand side of this equation in the form r cos 2x minus alpha. This is r using the expansion for cos A minus B, cos 2x, cos alpha, plus sine 2x, sine alpha. So that's r cos alpha, cos 2x, plus r sine alpha, sine 2x. Comparing this with the left-hand side here, we can see that r cos alpha equals 4 and r sin alpha equals 3. These are simultaneous equations to solve. When we get to here, r is always equal to the square root of 4 squared plus 3 squared, or this number squared plus this number squared. So r is 5. If we do 2 divided by 1, r sin alpha over r cos alpha, the r's cancel, and sin alpha over cos alpha is tan alpha. That's equal to 3 over 4. So alpha is the inverse tangent of 3/4, which is 36.87 degrees to the 2 decimal places required. In part D, we want to go ahead and solve this equation for values of x between 0 degrees and 180 degrees, which means for 2x we're going between 0 degrees and 360 degrees. We know from part C that the left-hand side can be written as 5 cos 2x minus 36.87 degrees, and that's equal to 2. So that gives us cos 2x minus 36.87 degrees is equal to 2/5. For the principal value, we have 2x minus 36.87 degrees is the inverse cosine of 2/5, which is 66.42 degrees. We're looking for solutions to 2x minus 36.87. So from here, 2x take away 36.87, we need to look for solutions between minus 36.87 degrees and 360 take away 36.87, which is 323.13 degrees. We can now use a cast diagram. A, S, T, C, 0, 90, 180, 270, and back to 360. We're going to look for our solutions from minus 36.87 all the way around once to 323.13. Our principal value is at 66.42. It's a cosine and it's positive, so the other one must be here, and by symmetry this is 66.42. So we start looking for solutions here, we go through 0, and the first solution we find is that 2x minus 36.87 is equal to the 66.42. We keep going, and the next solution we find is here at 360. Take away 66.42, so that's 293.58. We get back to the red line here, finding no more solutions. What we need to do is add 36.87 to each of these values. So 2x is equal to 103.29 degrees, or 330.45 degrees. Then divide by 2 and give to the 1 decimal place required. We get 51.6 degrees and 165.2 degrees, which you'll note is back in the range required.